Hi, we're in Chapter 8.2, the nature of covalent bonding. Okay, we have the oxygen we breathe, but we also have heard of the ozone. Remember the ozone layer and the hole because of pollution? Well, ozone is very different than oxygen. For one thing, you can't breathe ozone. And the other thing is that ozone is a combination of oxygen that's pretty unstable for the most part. Okay, it is O3 versus breathable oxygen, which we know is a diatomic molecule, which is O2. Okay, so O3 has a very strange structure. Okay, we talked about getting an octet or a noble gas configuration previously. So how do we get the octet in a covalent bond? Through sharing. So the sharing allows both or all of the atoms in the molecule to get their octet and get the electron configuration of noble gases because we count those shared electrons as belonging to both of the atoms in the bond. So when we count them, we will see 8 electrons around each of the atoms, but the ones that are in the bond will count twice because we'll say, okay, there's 8 there and there's 8 there. When we look at total number of electrons, of course, we just count the number of dots. So, for example, a single hydrogen atom has 1 electron. Okay, so let's do the Lewis dot structure for that. So we have here hydrogen with 1 dot, and I'm going to make this hydrogen with an X instead of a dot. And when they form a bond, this hydrogen has 2, this hydrogen has 2. Remember, hydrogen wants to be like helium, so it only has 2, okay? So now it looks like the helium configuration, so it's very stable. Combinations of atoms of the nonmetals, that's group 4 through 7, or 14 through 17, will form covalent bonds. And usually we'll get an octet. There are some exceptions to that where you get more than an octet, and that is lower in the periodic table due to the availability of d electron orbitals and f electron orbitals. But we're going to focus mostly on the octet. Okay, so what holds the hydrogen together? Well, it's the wanting to have that stable configuration, and they are being attracted by each other's nuclei, the electrons are, so that keeps them together. So 2 atoms held together by 1 pair of electrons is a single covalent bond. So to look at what that looks like, I'm going to try to show you with hydrogen again. I'll put the 2 electrons as dots this time. So we can write it that way, or as a single bond. Okay? So basically that's what I just showed you. There's a shared pair of electrons, so that's called a single covalent bond. So a structural formula is this one here, and we use dashes instead of the so a dash means 2 dots, which means 2 electrons. All right, so if we're going to look at how we put the single bonds together, we see that we have in fluorine we have 9 electrons. So if we look at this last group here, right here, these 2 electrons are being shared, so each fluorine basically appears to have a full second level. All right, so what we're doing is we're sharing these 2 electrons between the 2 fluorines. So that becomes our bond. These other electrons, if we're going to do our dots would just be like this. And if we think about that, that should add up to 6 electrons. 2, 4. Oh, this one doesn't count because it's the first level. 2, 4, 6. All right, so that's basically how we do it. Now fluorine, okay, since fluorine has these 6 electrons here, they will only share these 2 electrons. They can't have any more than a single bond. Okay, these up here are called unshared electrons, okay, or non-bonding electrons. So fluorine has 3 pair of unshared electrons. Okay, oxygen on the other hand has 2 pairs of unshared electrons, and then we have 2 single dots. So this is where bonding is available. So if we take 2 hydrogens, this hydrogen here will actually give up, well, not give up, it will actually share this electron. One of the hydrogens will share its electron, and the other hydrogen will share its electron here. And so we get an octet for the oxygen and a couplet for the hydrogens, and we can rewrite the bonding pair as that, a dash and a dash, and we leave the unpaired as dots. Okay, methane is carbon. Carbon has 4 valence electrons, so we need 4 hydrogens if we want to make methane. So each of these will give one to each of these orbitals, basically, and you get carbon with 8 and each of the hydrogens with 2. And then since they're single bonds, we can draw the little dashes. Okay, so if we look at it, the 1s is by itself for carbon, obviously. So what we're doing is we're sharing. Remember, what we did here is with carbon, we actually, since the 2s and 2p aren't too far apart, what we can do is we kind of hybridize these orbitals. Okay, so they're all of equal energy, and so these are the shared things. This is a little bit different. Usually would think we would see an electron here, but since they're all on the second level and there's 4 of them, we spread them out. Okay. Now carbon is interesting because it does not have to form 4 bonds. It can have what we call different degrees of hybridization. This is the normal electron configuration of carbon. Okay. So for single covalent bonds, we're going to have the S and P here, so we call this actually sp3, meaning we're hybridizing these orbitals into a new sp3, and we get that because there's an s and 3p orbitals. They're equal in energy. Okay, we're going to practice drawing some electron dot structures for you to take a look at. Okay, we make hydrochloric acid by dissolving hydrochloric gas in water. Hydrogen chloride is diatomic with a single covalent bond, so let's draw the electron dot structure. We'll go through this together. Okay, in a single covalent bond, we have to share a pair of electrons. We know hydrogen has 1 dot and chlorine has 7 dots, as seen here. So to come together, that hydrogen is going to move to where that single dot in chlorine is, and we get the hydrogen chloride molecule. And so hydrogen will look like helium, and chlorine will look like argon. Now, there are also things called double and triple bonds. If there are more than one space left on the relationship between the two atoms. They can form multiple bonds. So a double covalent bond is a sharing of 2 pairs of electrons or 4 electrons. Triple covalent bond is a sharing of 3 pairs or 6 electrons. So oxygen and carbon, oxygen has 6 valence electrons, carbon has 4. So there's room for actually making a double bond. So we have to play around with this a little bit. So here's our 6. These two are useful for bonding, okay? So they can bond there, and then this one can bond here, and we end up getting double bonds. Now, they do this very simplified. We would have to play around with this usually to see that the only way we can do this is by having a double bond here. I'm showing it to you now, but we'll go in more detail later on. And there's how we make a double bond. If there's 4 electrons, we have 2 sticks. Okay, triple bonds, nitrogens tend to form triple bonds. Okay, and that's so that you can get an octet. Let me just go through this a little bit while we're on this page. All right, because it's a little bit easier to see it with nitrogen. Okay, so if we have nitrogen, okay, and we could just do this. I'm going to use an X for that one, and X is for this side. There doesn't seem to be anything wrong with that, but nitrogens, these two, because how many do we have? We had 1, 2, 3, 4, 5. We had 10, okay? So we have 8 and 6 is 14, right? Well, that's too many. That's more than we actually have available, okay? So what we have to do, let me see, I threw that wrong. So what we have then is we've got nitrogen, which has basically 1 here and 1 here, and we're actually going to put this together.
What are you doing?
Recording a video. And so if we look at that, let's draw this again. We have 1, 2, 3, and the 2 there. So what happens is we have to bring these all down, and that's where we get that from. Okay, you might think an oxygen atom with 6 valence electrons would form a double bond by sharing 2 of its electrons with another oxygen atom. Okay? So if we look at these up here, right? These are available for bonding, okay? And that's what happens. These two will move down to the middle and form a double bond. So we have the same number of electrons as we started to. We have 6 and 6 is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have to have the same number of electrons we started with in our product, all right? And still obey the octet rule, and making double or triple bonds allows us to do that. So anything in group 17 will form single covalent bonds. Okay, so there's 3 of our diatomic elements. Tells you a little bit about each of them. I'm not going to read it to you. I'm going to wait on this slide for a second for you to get a chance to read it. Okay, this will be a question for you. So please answer it on play pause it. So the octet refers to the 8 electrons that every atom wants to have around it so it obtains a noble gas configuration. Okay, there's something also called coordinate covalent bonds, and they're a little bit different from other types of covalent bonds. Carbon monoxide is an example of a type of covalent bonding different from seen in water, ammonia, methane, and carbon dioxide. It's possible for both carbon, which needs to gain 4 electrons and oxygen, which needs to gain 2 electrons to achieve noble gas electron configuration by a type of bonding called coordinate covalent bonding. So let's look at what happens. If we look at this, we have carbon, and we get the double bond here. So we have 8 for the oxygen, but we only have 6 of the carbon around carbon. So if we actually do the following, we borrow 2 of these electrons from the oxygen and form a triple bond, then everybody's happy. So the reason we call it coordinate covalent is it's actually getting extra electrons from an electron pair on one of the other atoms. Okay? So it's not 1 for 1. And that's where we get the idea that it's coordinate covalent. Okay, so in other words, the 2 electrons used in the bond come from only one of the atoms rather than 1 from each of the atoms. Okay, ammonium ion, okay, consists of atoms joined by covalent bonds, including a coordinate covalent bond. So it's also called a polyatomic ion. Now what a polyatomic ion is, it's an ion that's contained of more than one type of element. Okay? And it's an ion because it has a charge. The reason it has a charge is it has an extra electron or one or less than an extra electron. It could have more than one electron too, and it has more of a negative charge. And the reason that it forms is because of this unshared pair right here. Okay? This unshared pair of nitrogen, okay, is going to attach itself to a proton, okay, a hydrogen ion. And so this hydrogen ion is going to attach itself to this proton. Okay? This proton is going to attach itself to the ammonia molecule. All right, so we have then a positive charge because now all of a sudden, if we count up all the electrons, we have one less than we started with because this here has a positive charge, but we're using this. So if we went around and looked at everybody, they don't have as many as they should. So we end up with a positive charge. Now this here is coordinate covalent because both of these electrons have come from the nitrogen. Okay, polyatomic cations have covalent and coordinate covalent bonds because they usually have extra electrons. And also, polyatomic ions include both ionic and covalent bonding. So how would we draw the electron dot structure for such a species? Okay, so hydronium ion, okay, is H3O plus, which means it's a water molecule with an extra hydrogen. So we have oxygen. Oops, let me put the pen on. Well, we're gonna go through that, so I won't draw it. Okay, so we think of how many electrons each of the species has. Okay, well, we've got water already, so we can write the water molecule as is. And the hydrogen ion comes along and is attracted to these dots or electrons in the oxygen, and it basically forms a coordinate covalent bond. So the fact is now that this is positive, okay, because these electrons are belonging to the oxygen, but the hydrogen picks it up, and the whole species becomes positive. Notice we put brackets around it and puts the charge on the outside. So the positive charge is because the hydrogen ion is attracted to the neutral water molecule, and since it's positive, that positive charge is going to be there. Okay, I'm going to ask you this question on play posit. No, because coordinate covalent bonds exist where the shared electron pair comes from one of the bonding atoms. Okay, what are some exceptions to the octet rule? Okay, the octet rule cannot be satisfied in molecules whose total number of valence electrons is an odd number. You have to have an even number. There are also molecules in which an atom has less or more than a complete octet of valence electrons. All right, two plausible electron dot structures can be drawn for NO2, which has a total of 17 valence electrons. It's impossible to draw an electron dot structure for NO2 that satisfies the octet rule for all atoms, yet NO2 does exist as a stable molecule. So this is an exception, NO2. And as I said, some molecules that are like sulfur is near where there's d orbitals available, empty ones. So we have an extended octet. So something like SF6 can occur, and that means instead of having 8, we have 10 electrons. I'm sorry, 2, 4, 6, 8, 12 electrons around the sulfur. That is the question that I want you to think about and answer. On play, pause it. No, because we just mentioned NO2 does not apply the octet rule. And we also talked about SF6. Okay, we can also determine the strength of a covalent bond by looking at something called bond dissociation energies, meaning how much energy is it required to break a bond. Okay, or combine them. Okay, they're kind of like interchangeable. A large quantity of heat is always released when hydrogen atoms combine to form hydrogen molecules, and the release of heat suggests that the product is more stable than the reactants. Okay, so what happens is when you form the bond, energy is released. So the bond dissociation energy would be 435 kilojoules to break that bond apart. Okay, so bond dissociation energy is usually in kilojoules per mole, and it's the amount of energy to break 1 mole of bonds of a compound. So the thing that you can think of is the amount of energy you need to make released would be the same amount, but a negative number. A large bond dissociation energy means it's a very strong covalent bond because you're going to require a lot of energy to break them apart. A single bond for carbon is 347 kilojoules per mole, so that's why carbon compounds tend to be so stable. Okay, again, you can describe this because the dissociation energy is so high. Here's another question for you. A strong covalent bond has a low bond dissociation energy. True or false? Play pause it. False. A large bond dissociation energy corresponds to a strong covalent bond. How many resonance structures used? Resonance means that if something could have more than one Lewis dot structure, we can actually say it's flipping between these. Okay, so if we look at ozone, the double bond could be on the right or it could be on the left. So we draw this arrow in between to represent ozone, flipping back and forth between the two. In some ideas, instead of a double bond, sometimes you'll see this written as a bond and a half to show that it's resonance, because does it actually exist in this flipping flopping state, or is it actually a stable state that is somewhere in between? But this is the best way to show this. So as I said, we used to think they flip back and forth to resonate, but we actually use double-headed arrows to show that. What's really probably happening is it's like a bond and a half, because we know of the way the electrons go around the atoms. Okay, as far as size goes, double covalent bonds are usually shorter, so they're tighter. And so we thought the bond lengths in ozone were unequal, but we've shown through experiment that they are equal. So in actuality, as I said, the bonding is a hybrid of these two extremes, and so I sometimes call it a bond and a half rather than a double bond, but there's no such thing as a bond and a half. It's just a way of thinking about it. Okay, we still call them resonance structures because this is the only way we can actually draw it. Okay, and resonance structures are structures that occur when it is possible to draw 2 or more valid electron dot structures that have the same number of electron pairs for a molecule of an atom. Very important fact. Okay, and basically the resonance structures allow us to represent the structure of something that's very hard to describe in a single structural formula. Okay, I'm not going to ask you this one because this is a little bit tricky. The answer would be no, because they're a way of looking at it, but the actual bonding is kind of a hybrid. It's not flipping and flopping. Okay, here are some of your key terms to remember from this section. Make sure you take these down and stop the video. Okay, that's it for this video. Have a good day.